A very good afternoon to my students. So I am here, Dr. Anirban Chakraborty from Department of Computer Science of our beloved Barakpur Rashtraguru Surendranath College. So today I want to give you a glimpse on introductory concept on digital electronics and rather digital circuits I will discuss here. So as the name suggests here, today I will concentrate on digital circuits. Just here I will give some glimpse on digital circuit, a very basic concept. Those who of you are totally ignorant regarding this field, don't worry, I am starting from the scratch. So what is digital? Nowadays, previously suppose the clock, we were aware of this like of clocks, means suppose it's 10:15. So when this larger arm from 10:15 is moving to 10:20, what was happening? It was sweeping all the points from 10:15 to 10:20. This is the concept of analog, where between 2 points there exist indefinite number of points. Means you can't define how many points will be there between these 2 points. So this is just the analog clock, which was just running from colloquial time. Nowadays, just if we observe the clocks displayed on the platform, what is there? There this like of time is being displayed 10:15. Now when just the time is 10:16, obviously it shows this like, means here the difference from the previous is that here from 10:15 to 10:16, when the arm is sweeping from 10:15 to 10:16, it was getting enormous amount of points, indefinite amount of points. However, here there is a jump from 15 to 16, either 15 or 16, no intermediate points between these two. So this is the concept of analog versus digital. Now again, to explain this concept, I can give you another one very practical example. What's that? Suppose I want to go from this point to this point. Two things are there. There are stairs, just which is very common for us. Another one is this like of sloping may also there. Stairs we see everywhere in our home also. These slopings also generally nowadays we can observe them in any public places, mainly for physically challenged people, or in platform, railway platform. To go into the platform, we just go across this like of sloping. What's the difference? In this sloping, here you can stand here, you can stand here, you can stand here, means each of the point you can just be there, means there is a continuous movement from this point to this point. However, if you go to the stair, either you can stand here or you can stand here. No way you can't stand at this point, means either here or there, there is some discrete values, discontinuous values. Previously it was just the analog concept, and now I have jumped into the digital concept. So what is the necessary of discussing these digital circuits? Because if I tell that just we have nowadays living in an era of automation, then I am not uttering anything wrong, because just your computer and smartphone are there. Along with these two, if you consider anything of your daily use, like your washing machine, just what you do? You just put your clothes into the washing machine and just fix its switch. Suppose you want to wash up your curtain cloth in 60 degrees centigrade. So, you just make your switch on and just engage yourself into the household work. Rest of the thing automatically is being done by your washing machine. Means just decides how much water to take, next when to mix up the detergent, how much time it has to mix up, how much time it has to rinse, etc., etc., how long it has should be dried, everything. Means there is a glimpse of automation. And where there are this like of circuits in your microwave, in your computer, in your washing machine, these digital circuits come into play. Now, along with this digital circuit, the main concept which obviously we should know is the Boolean algebra. In our traditional mathematics, what we learn? We have learned any numbers. Means suppose we have learned this like of numbers 1, 2 or 3, 5, 6, means all the numbers they are composed of digits 0 to 9. Means when we want to represent any number, we take help of these 10 digits 0 to 9. However, the basic difference in Boolean algebra is that we will do everything what we had done there, any arithmetic we will do here, but using only two values 1 or 0. There are two concepts, positive logic and negative logic. Here majorly we follow positive logic. Positive logic means every high, every good, every positive is represented by 1. Means when just you want to represent a light is going on, or the students got passed, or the gate is open, every of these is being represented by 1. And the reverse, the light is not glowing, the student has got failed, or the gate is shut, everything this is represented by 0. So, anything will be represented either by 1 or by 0. This is the basic of the digital circuit. So, to learn digital circuit, we must possess some knowledge on logic gates. Gates means just at this point, I can tell you that gates are nothing, just some circuits which have some inputs through which we feed voltages and output where it's giving out the output voltage. These are the gates. First one gate which comes upon the crease is the OR gate. Here this symbol represents that whenever anywhere you observe this symbol, this represents that you are talking on OR gate. Now these lines are known as the input lines, means you are feeding input through these lines and you are getting output through this line. Now the difference with main analog circuit and this like of digital circuit is that in analog, when you are getting value, suppose 4.5 and someone is getting value 4.7, obviously these two are not equal. According to analog circuit, they possess a huge amount of difference. However, in digital what is there? These are circuits, obviously they require some voltage for their operation. Suppose I am using a battery of volt plus minus 5 or just highest voltage is plus 5 volt. So, a battery which can at best give me 5 volt. So, if I am operating this OR gate using that one battery, what's there? Here at output either you may get voltage more than 3.82, means you may get voltage 3.9, 4, 4.0, 1, 4.5, etc., etc. And according to the digital logic concept, all of these are same. Means I have told you at the beginning that digital logic works only on two values, either 0 or 1. So here, what's there? Here I am getting value more than 3.8, means it will be inferred that you have obtained output value as 1. So, here in digital logic concept, when someone is getting value 3.9, someone is getting value 4.4, someone is getting value 4.2, everything is same. Similarly, in analog concept, when someone is getting value 0.2, when someone is getting value 0.3, there possess a huge difference, but in digital, all the values here would be assumed as 0. So, 0 means here not the perfect 0, the lower bound is there, just consider it as 0.5. So, any value less than 0.5 would be treated as logic 0, and any value more than 3.82 would be treated as just value as logic 1. Here the name, just in the previous slide there was a name logic gates, means not using the exact value, they are using the logical concept, means logical level 0 or logical level 1. So, what is the nature of this circuit or OR gate? Here, look, these are the input lines. Here I have drawn only two input lines. An OR gate at minimum possesses two input lines, but at maximum logically it may contain 10, 20, 100 any number of input lines. But the output line of an OR gate is obviously always 1. So, what is the logic of its operation? Here the logic of its operation is that here the output obviously may be either 0 or 1, because it is working on the basis of the Boolean concept. Here the output goes to 0 when all the inputs are 0, means when all the inputs are at logic level 0, then only the output would be 0. And if any among the inputs is at 1, the output becomes 1. Means suppose you have a OR gate which has suppose 20 inputs. So, among these 20 inputs, 3 inputs are 1 or any one input is 1. No matter, just at least one input is 1. So, I will put 1 at the output. If I found that all the inputs are 0, then only I would offer 0 at the output. So, it is written as a plus sign next B. Here it is uttered as logical OR, means A or B, means it would be written as 1 or 0 equal to 1, 1 or 1 equal to 1. So, this is not a plus operation, it is just the logical OR operation. Next, I am moving to another one circuit or logic gate. This is the AND gate. Just like previous, here I have drawn a 2 input AND gate. 2 input AND gate, here I have drawn again like OR gate. An AND gate have minimum of 2 inputs and just a single output, minimum of 2, means here also just like OR gate, there may exist any number of inputs greater than equal to 2, means 2, 3, 4, 10, anything is possible. The working methodology of the AND gate is what? When all the inputs are 1, then only its output become 1, means among its input, if at least any one is at 0 level, then its output is also at 0 level. Means suppose you have just got at your question paper that there is an AND gate which has suppose 20 inputs. So, you have to determine its output. So, how? Just I will look just any condition when all the inputs are 1, then only at the output of the AND gate I will put 1. In any other means when not all the inputs are at 1, means at least any one is at 0, just like here A is at 0, here B is at 0. So, for these cases the output is at 0 and here all the inputs are 1, so output is also at 1. Next, I am moving to another one gate. This is known as the NOT gate. Unlike the previous two, the main thing is that here in OR gate and AND gate I have told what? I told that for input there may be any number of input lines greater than equal to 2, means 2, 3, 4, 10, 50 etc. But here input line is always 1 and output line is also 1. Here input line 1 means only a single input. This means either you can give you here 0 or 1. The property of the NOT gate is just it is making the input opposite, means when you are giving 0 means logic 0, output is at logic 1, and if the input is at logic 1 then the output is at logic 0, means just it is changing the input from 0 to 1 or 1 to 0. Here it is the notation A prime, A bar, or you may observe in some books A prime is there, one just single quote like thing is there. So, whatever be there, this like bar or that like prime means there is a presence of NOT gate, means A prime or A bar means just whatever is the value of A bar is just opposite to this, means if A is 0 you have to write 1. So, this is the symbolic represent of NOT gate, and I have told that bar means presence of NOT gate is there. So, OR gate, AND gate, NOT gate, these three gates are just known as basic gates, means when you want to just construct a digital circuit, how much large it is does not matter, everything could be done using that 3-1 gate, just AND or NOT gate. So, these are known as the basic gates, fundamental gates, means anything could be achieved with the help of these three. So, we have to keep in our mind their notations and their this like truth tables well. Next, after completion of this fundamental concept, I am moving to the another one gate, NAND gate. This NAND gate has a very good application in today's lecture. I will tell it later, just now I will explain its behavior. First look at structure. Look, here there is a bubble. Bubble means just there is just a, in NOT gate there is this like a bubble. Look, in NAND gate also there is this like a bubble is there. This means that here there is a presence of NOT gate also in this gate. Whenever in any circuit, whenever you observe this like a bubble is here, just you consider there is NOT gate in the circuit. Somehow it is got sandwiched with some other gates or like that, but it is there. So, first one is the this portion before bubble, it is the AND gate, and next after AND gate there is the NOT gate. So what is the nature of the NAND gate? Actually the NAND gate, N next AND, N means not of AND means just it behaves fast like an AND gate. Next the output is inverted, means that output is passed through the NOT gate. Here the concept is just like, first consider that it is just like an AND gate. So whatever means if all the inputs are 1, then I will get 1 in AND gate. However, here the output is passed through the NOT gate, so it will be reverse. In other word, for AND gate where you will achieve 0, for NAND gate you will achieve there just 1 or vice versa. Means in AND gate what I have told? In AND gate just I have told you when all the inputs are 1, then only you will just get at output 1. Here just reverse, when all the inputs of the gate are at 1, then only at output you will get 0, means it is working just opposite to that of the AND gate. So just other properties are same, means here like AND gate it will also have input minimum to maximum at per your need, and output obviously is 1. And how it would be represented? AND is represented A dot B, and if we omit dot, just it is assumed that dot is there, means it is AND gate. So here after AND there is one NOT gate, so we are using this like a bar. So NAND gate means if the inputs are AB, then output is AB bar. If the inputs are ABC, then the output is ABC whole bar. This like. Next, just I am making a review of this concept what we have learned till this point. First one is NOT. Generally, I have mentioned that NOT is a horizontal bar, or in some books there is used one prime. So 0 bar means ones and 1 bar means 0, means whatever is the input, if I am applying a bar here, then it will be just reverse. Or means just a plus sign is there, but we will utter it as or. 0 is 0, means when both of the inputs are 0, then only I will get 0, else 1. In AND, just the concept is that when all the inputs are 1, then only I will get 1, else I will get 0. So here star or dot is written, means in some books 1 star 1 is written there, in some books 1 dot 1 is written. Just don't get confused, everything is same, means just the concept of AND. Now here are the some commonly used logic gates, just what we have learned. First one is NOT. So I have told NOT, what apply, you will get its complemented value. If 0, output is 1, if 1, output is 0. Next one is AND. Here AND means just when all the inputs are 1, then its output are 1, else its output is 0. And next one is OR. OR has the this like of notation. Here also inputs may be 2 or more. If all the inputs are 0, then only output is 0, else the output is 1. Now AND gate, OR gate, NAND gate, they may be 2 input, 3 input, 4 input, etc. So here I have just shown you another gates, 2 input OR gate, 3 input OR gate, 2 input AND gate, 3 input AND gate. And here just how many inputs are there? X, Y, Z, W, just you have to write it X plus Y plus Z plus W in this way. Next one is the NAND gate. NAND gate is just in those positions where AND gate produces 0, it produces 1, where AND produces 1, it produces 0. Means in AND gate, when all the inputs are 1, then only the output is 0, means just opposite to that of the AND gate. And when AND gate produces 0, means if at least any one of the input is 0, then the AND gate is generating 0. In those cases, NAND gate is generating 1. Next one is NOR gate. NOR gate, just in the way AND and NAND is connected, just using the same logic, OR and NOR is connected. Means here again look, there is a bubble, means just OR gate is here and next there is a NOT gate. Means for the inputs when OR generates 0, NOT generates 1 and vice versa. Means in OR, when all the inputs are 0, then only it produces 0. For NOR, when all the inputs are 0, then only it produces 1. And if at least any one of the input is at 1, then it generates 0. Just unlike OR, where for those cases it generates 1. Final one is XOR. To determine the output of XOR gate, we have to just mention one property. Its name is parity. Although the term seems quite new, but it is not a very hard concept. Means like this AND or not NAND, here also number of inputs are 2 or more. Now suppose your XOR gate has 10 inputs. So you have to count how many among these 10 inputs are at logical 1, means how many ones are there. Suppose among these 10 inputs, 6 inputs are 1 and 4 inputs are at 0. So 6 inputs are at 1. This means that 6, it's a what? It's an even number. So when at the input of XOR gate even number of ones are present, then the output is at 0. If odd number of ones are present there, the output becomes 1. So among the 10 inputs, if suppose I am applying 9 inputs as 1 and 1 input at logic 0. So 9 inputs are at 1, means odd number of ones are there. So output is at 1. And suppose 4 inputs are at 1 and 6 inputs are at 0. So 4 inputs are at 1. 4 is an even number. This means the output will be 0. So this is the concept of XOR gate. So now based on the previous concept, just now I will draw some circuits when some equations are given. So suppose find the output of the following circuit, means suppose at your question paper this like of one circuit is there, you have to determine the value of the output. So first, what is there? Here first one is there, I have observed that there is an OR gate. So OR gate, its input is X and Y. So What would be its output? Obviously, as x and y is the input, its output is x or y. So, this like. Now, for this NOT gate, it's getting input y, so its output would become what? Its output would become y bar. So, this x or y and this y bar both are being fed as input to this NAND gate. So, what will be its output? Its output x or y dot y bar like this. So, this is the just for your perusal I have broken it, means here y has been shown you separately for your understanding purpose. Now, another one example is there. Suppose this is an expression just like the previous. In previous what we did, just there was a circuit and finally we found what would be the output. Here output is given, you have to find out the corresponding circuit, means this is the output given. So, first look how many inputs are there, x and y, two inputs are there. So, just I have to note two inputs, first one is x, another one is y. So, x line, y line. What is first? X is not being fed directly, there is x bar. Bar means what have I told? Means NOT gate. So, there is NOT gate. So, I have obtained x bar. Next, x bar I have found, y is there. So, this x bar and y have to fed, there is a plus, means into an OR gate. So, it would be like this. So, this is the corresponding circuit of the given expression. Next one example, here x or y, this has been a whole bar is with x. Nothing is there means we will assume that there is one dot means AND gate. So, again how many input lines are there? Two variables x and y. So, first of all we have to consider only two input lines x and y. Next what? First operation is x plus y, means x or y. So, there should be a presence of OR gate. So, x or y. Next, this x or y I have obtained. So, I have to make it bar, means there should be one NOT gate. So, there is the NOT gate x or y whole bar. Next, x or y whole bar I have obtained, here is the x. So, dot means just AND operation. So, I have to found one AND operation, this one with x like this. So, this is the final output and the corresponding circuit I have constructed. Similarly, this is quite easy now for us, x bar plus y, two variables x and y. So, first I have to do the NOT operation, x OR, next the OR operation, logical OR means plus. So, x bar or y. Now, up to this point we have done realization of an expression or anything using just what? Using basic gates, means we have made use of three types of gates. So, what is the problem here? Means these gates AND or NOT, they are just, if I implement it in the practical circuit, we have to purchase the corresponding IC chips, integrated circuit chips. What are they? I am not telling, just at this point I can mention you this much, that when I want to purchase, suppose an OR gate, what? Two input OR gate, what I have to do? Just I have to purchase the corresponding IC 7432. Now, what it consists? it consists of 4 2 input OR gates. So, if I consider an circuit just like this one circuit, here I have used only one OR gate and only one NOT gate. So, what's here? I have purchased the IC of OR gate, means I have purchased 4 OR gates, because in one IC there are 4 OR gates. Among these 4 I have used only one. So, rest 3 got wasted, and in the IC of NOT gate 6 gates are given. I have used only one. So, 5 been wasted. So, as a whole 3 plus 5 means 8 gates been wasted. I have used only 2. And another one thing is that I have to purchase 2 type of ICs. If there is AND gate also, 3 type of ICs. Now, NAND gate is universal gate, means I can realize any one circuit using NAND gate only, no need to use any other type of gates. So, the thing is there, just if I want to implement, I will only purchase the IC for NAND gate, and their wastage will also be less. Just I will show you how. Here I must learn one concept of bubble cancellation law, means in general mathematics, suppose a number is there 2. So, if I add just 2 minus sign, negative signs, then what would be there? Again I am returned back plus 2. So, just I can use 2 negative signs one after another safely, no changes in the value would be there. Similarly, just according the property of NOT gate, if 0 is supplied, it is applied to one or NOT gate, then I will obtain 1. Again one NOT gate is there, again I will return back 0. Means if 2 NOT gates are there one after another, I will get back the original value without any change. So, applying nothing or applying to NOT gate one after another are just synonymous. So, I can easily use this. Using this trick, we have achieved our goal. How? Before going into that, first I have to consider one law, that is De Morgan's law. In De Morgan's law, what's there? Just first one is telling me A dot B whole bar is equivalent to A bar or B bar. What does it mean? Just first I have constructed the truth table, means all possible values of A and B, A0, B0, A0, B1, A1, B0, A1, B1. So, what is the value of A dot B? Just applying the concept of AND gate, it takes only 1 when all the inputs are 1. So, here I have put 1, all others 0. So, if I am making it complement, means applying one NOT gate, zeros will be 1 and 1 will be 0. So, it is the left hand side of the De Morgan's law. Again, here I have made A bar, means where A is 0, A bar is 1, where A is 1, A bar is 0. Similarly written B bar, where B is 0, B bar is 1, B is 1, B bar is 0. Now I done what? A bar or B bar. Or means if both are 0, then only output is 0. If at least one is at level 1, then output is 1. So, it's seen that the red color columns are carrying same values. So, left hand side of the De Morgan's law, this is the right hand side of the De Morgan's law, and using the method of truth table, we have proved that the De Morgan's law hold. Now, here is the De Morgan's law. Just here I have written, and I now would like to draw the left hand side A and B. So output is AB. Here I have applied one AND gate. Now there is one NOT gate. So I have obtained AB whole bar. So just I have drawn this using basic gate. Now suppose I have pressed it so that this NOT gate got sandwiched with this AND gate. So it becomes what? Look, the structure becomes of a NAND gate, means AND has got sandwiched with that NOT gate. This bubble is signifying me that there is one NOT gate. So De Morgan's laws, first law's left hand side is nothing but the NAND gate, and for right hand side just A bar or B bar. So here is the A bar, here is the B bar. Again I am making them sandwiched. So this bubble goes here, this bubble goes here. So how would it look? It would look like this, and this is known as bubbled OR gate. So De Morgan's law of left hand side is, first law's left hand side is NAND gate, right hand side is bubbled OR gate. Means these two gates are working in a symmetrical way, means just I can replace any one in case of other. Now just I would now represent NOT gate using inverter, sorry, NOT gate using the NAND gate. Means here is the NOT gate. Now NOT gate means if input is X, then output is X bar. So what we have done, the both inputs of a two input NAND gate been joined together. So if you supply X, both are getting X. Now in case of AND gate, X dot X means X, means if both are 0, then output is 0. If both are 1, output is also 1. Means just if there is a simple AND gate, then the output is X. But this is a NAND gate, means there is a inverter, so the output becomes X bar. So here if you apply X, you will get X bar. Means single input NAND gate is nothing but the NOT gate. To realize AND gate using NAND, just I have first drawn the AND gate, this I have to realize using NAND. Next one, just applying the logic of bubble, here I have drawn one bubble, here I have drawn one NOT gate. They are cancelling each other. So just actually we are doing nothing, but this is the NAND gate and NOT means single input NAND. So here is the final. So here we have realized NAND AND gate using NAND gate. This is the OR gate. Now it has the similarity with bubbled OR gate. So here only two bubbles are missing. So just we have drawn these bubbles in this way using bubble cancellation law. So this bubble got cancelled with this NOT gate, this bubble is cancelled with this NOT gate. Means we have done nothing actually. Now this is the bubbled OR gate, means this is equivalent to NAND gate, and these two NOT gate are just what? Single input NAND gate. So here this is the OR gate which we have realized using only NAND gate. So these are the equivalence what we have studied. This is the equivalence of AND gate using NAND, OR gate using NAND, and NOT gate or inverter using NAND. Now suppose this is the circuit. So here all the three types of gates are there. I want to realize this expression. So using the previously learned mechanism, I have drawn this, means just I want to realize this using the basic gate. Now my motto is to realize it using NAND. So what would I do? Just I have applied the bubble cancellation law here and here. So what's there? It is NAND. It is NAND. Bubbled OR means again NAND, and NOT means single input NAND gate is there. So finally I have achieved everything using the NAND gate. So here also beneficial in terms of gates also. Here I have to purchase one chip for AND, one chip for OR, one chip for NOT. Wastage is there. Here in this chip 2 are used, so 2 wastage. Here only a single is used, so 3 wasted, and here only 1, so 5 wasted. But when I have realized it using NAND, I have used 4. So just the IC where there was 4 NAND gates, I have used all of them. So in terms of financial benefits also, we are higher here. So it is thus the I have proved the equivalence, that using NAND gate also the circuit is working fine. Now realization of another one circuit is that, first one is that this is the problem of staircase switch, means just at our home also this switch exists. The light is in between of the stair, means when you going from ground floor to first floor, just you are making on the light from ground floor, and from first floor you can making it off or the reverse. So working strategy is that the light is on only when the switches are in opposite position, means either this off, this on, or the reverse. But when both the switches are off or both the switches are on, the light does not glow. So this is the truth table, means when both the switches are off or both the switches are on, the light is off, else the light is on. Now 2 switches means 2 variables. So how to write the expression? In expression what's there, I will consider only the output columns corresponding to those rows which is producing output 1. So like this and this, second and third. So here A's value is 0, so it is written as A bar. B is 1, so it is written as B. Here A is 1, so it will be written as A, but B is 0, it would be written as what? B bar. So the expression is for this row A bar B, for this row A B bar, in between I would add one plus sign. So this is the final one expression, A bar B plus A B bar. Now I have simply drawn it, A bar B, A B bar, and these two been fed into an OR gate. So now I am applying bubble cancellation law here. So after applying the bubble cancellation law, it is there. So this is NAND gate, this is NAND gate, this is bubbled OR gate, means just NAND gate, and these two NOT gates means just these are what? Single input NAND gate. So this is the final one circuit which we have achieved or realized using only NAND gate. Final one example is this. A university has a circular boundary wall with 3 entrances. Authority has decided not to open 2 consecutive entrances, and we have to realize it using only NAND gate. So here is the nature of the university boundary walls. It is in circular and 3 entrances A, B and C is there. Now how to write the truth table? In truth table, how many rows are there? If there are 2 inputs, there are 2 to the power 2 means 4 rows are there, just like in the previous example. Look, there were 2 inputs A and B, so 2 to the power 2 means 4 rows are there. Here how many inputs are there? 3 inputs are there, A, B, C. So the number of rows 2 to the power 3 means 8. If you have 4 inputs, then your number of rows 2 to the power 4 means 16. So for n inputs, your number of rows are 2 to the power n. Now actually, those who knows the binary number system, here I have to fill these 8 rows, they would be filled by binary values of 0, binary value of 1, binary value of 2, binary value of 3. up to binary value of 7, means 0 to 7. But those don't have knowledge of this binary number system, don't get tensed. How would we fill up this? Just I have to fill it here 4, just 8 rows. So I would make it half, 4 zeros, 4 1. Next 2 zeros, 2 ones, 2 zeros, 2 ones. Means first 8 is divided into half, 4 4, 4 zeros, 4 ones. Next again half, 2 zeros, 2 1, 2 zeros, 2 ones. Next again half, single zero, single one, single zero, single one. And I will achieve this truth table, input part of the truth table. For 16, if you have 4 inputs, you have to fill up 16 rows, then 8 zeros, 8 ones. Next 4 zeros, 4 ones, 4 zeros, 4 ones. This like. So, not to worry. So, for the first row, what is there? All the gates are closed. Is it valid? Yes, valid, because at night time or when there is the holiday, so all the gates are closed. So, this is valid, means 1. Here only C is opened, so valid. Here only B is opened, so valid. Here look, B and C is opened, B, C, 2 consecutive gates are opened, invalid situation, so 0. Here only A is open, valid. Here A and C is opened, A and C, they are consecutive because it has circular wall, so A and C, so invalid. Here A and B consecutive, so invalid. Here all the 3 means AB or BC, many consecutive pairs, so obviously this is invalid. So here how many 1 terms are there? 1, 2, 3, 4. So at the output expression I will get 4 terms. First one A bar, because for A it's 0, B bar, for B it's 0, C bar. So A bar, B bar, C bar for this. Here A bar, B bar, C. Next one A bar, B, C bar, and next one comes here A, because here it's 1. So I will not put any bar, A, B bar, C bar, and all these 4 terms would be joined by logical OR, means plus. So this is the final expression. So this, look what just I have told. First one is A bar, B bar, C bar. Next one is A bar, B bar, C, A bar, B bar, C. Next one is A bar, B, C bar, A bar, B, C bar, because B is at 1. So I am not putting B bar, it is A bar, B, C bar, and finally it's A, B bar, C bar. For this A is at 1, so A, B bar and C bar. So this is the final expression. I have drawn it just like previous concept, A bar, B bar, C bar, A bar, B bar, C bar. I have made A bar using this NOT gate, B bar using this NOT gate, C bar using this NOT gate. So first one is producing A bar, B bar, C bar. Next one A bar, B bar, C. Third one A bar, B, C bar, and the fourth one what? A, B bar and C bar, and there are plus means OR, so I have fed into OR gate. So this is the final output here. So just using the concept of bubble cancellation law, we have cancelled them up, means 2 NOT gates cancelling each other, we have achieved the goal. All of these are NAND gate, this is bubbled OR gate, although it has 4 inputs, so this is 4 input bubbled OR gate, means 4 input NAND gate, and these are just NOT gates, means single input NAND gate. So this is the final. So here I have achieved my goal using only NAND gate. So with this lecture, with this point I am finishing up. So what we have learnt in this lecture? First one, a brief review on Boolean algebra. Next one, we got some concepts on basic gates and their truth tables. Basic gates means or and not. Next we learned De Morgan's law. Although there are two De Morgan's law, but in this session we have given thrust only on the first law because we have applied the circuits using NAND gates. Next we learned concept of NAND gate as universal gate, means any gate been realized using NAND. First we realized the basic gates, means OR and NOT gate using NAND gate. Next we learned the fact that if any circuit is there, first we drawn it using basic gates, next we have converted it using only NAND gate. So a big thank you